Okay, we are now recording and we are live on Facebook. So I'd like to welcome everybody to our CWrap conversations with rotary action people. Today we have a very exciting show in line with you. I'm looking at Larry Metcalf's brief bio, and I'm going to just read that to you. It caught my eye very well. He's a retired flavor chemist. He spent 30 years doing beverage R&D for Coca-Cola. He now does solar astronomy presentations at mainly elementary schools and middle schools in the Columbia area. It's a completely free program. Typically, Larry visits 40 to 50 schools each year and over 10,000 students a year. And they get a chance to look through two powerful telescopes at the sun in a safe manner. He is a NASA Solar System Ambassador, which is a really cool title. So Larry, I'm going to turn it over to you and let you share your screen and tell us your story.
All right. Here we go, Sharon. Well, thank you for the kind introduction. And what we're going to do today is perhaps something a little different. I wanted to talk about the James Webb Telescope, and specifically maybe from a different point of view. There's been a lot of news about the James Webb Telescope. It's successfully launched, and there are lots of images and snippets, but I think maybe perhaps people don't have the background understanding of where it's going and why it is so important. This opening image is actually a picture of the James Webb Telescope as it is now in space. But let's go back up a little bit here to, there we go. So the James Webb Telescope is specifically a successor to Hubble. It's not a replacement. The Hubble is actually still working, and it does still provide very valuable information. The big difference is the James Webb Telescope is going to observe the universe in infrared light, whereas the Hubble mainly does visible light. It's also going to be 1 million, and it is now 1 million miles from Earth. So it will not be user serviceable like the Hubble was. You know, we went up and fixed the Hubble, and we adjusted the Hubble and improved the Hubble on several occasions with the space shuttles. But this will be over 1 million miles away instead of orbiting the Earth. And there's some good reasons for that. Backing up just a bit to get everybody grounded, the Hubble, this is a picture of the Hubble. You can see the Earth below it. The Hubble orbits, takes about 90 minutes to come around. You can actually get an app on your phone, and it will tell you when the Hubble is going to go overhead. We've seen it numerous times. It shortly after sunset, if it's passing overhead, that reflective coating reflects the sunlight, and you can easily spot it just with the naked eye, actually, going over South Carolina. I think, personally, this is the most fascinating part about the Hubble telescope.
Now we see the Hubble telescope deep field image.
Okay, but now do you see the one before it?
We do now, yes.
Okay. So that was, I talked through that, I'm sorry. And then there's a picture of the Hubble and the reflective. I don't know what was wrong. Anyway, but we're all up to speed now, right? I apologize for that. I don't know what was going on. Everybody can see the one that says Hubble Telescope Deep Field Image?
Yes.
Okay. This is the thing I think that they did that was absolutely phenomenal, that really hit home, to show the power of having a telescope in outer space where you did not have to deal with the atmosphere and ambient light and so on. So this is just a picture that's a chunk of the night sky that actually doesn't have very many stars in it. And the outer square box was the first place that they were looking. And then the smaller square box in the middle is a point at which it took some scientists several years of lobbying to get the administrators to point the Hubble at that small square, which appears to have a few faint stars in it. And they began imaging and they came up with the most famous of all images. That is that exact same spot. That's that spot. And everything you see, there's literally hundreds of galaxies and solar systems and stars, just incredible, in this little black spot, little box that appeared to have nothing in it. So that just shows you the power of getting a telescope out from Earth's atmosphere. So I think it's important to understand this chunk because they talk about it a lot. A telescope, in a sense, and that's why I put it in quotes, looks back in time. You're seeing that slide now that says looks back in time? Okay. All right, good. So the light from the sun takes about 8 minutes and 23 seconds to get to Earth. So when we're viewing the sun, like at our solar astronomy presentations, you're actually seeing what happened on the sun 8 minutes ago. So in a rudimentary sense, you are looking back in time. Let's take another example. This is one that amateur astronomers and professionals alike are very interested in. There's a big star in the constellation Orion called Betelgeuse. It would be his upper right-hand shoulder. It's right here, and it's reddish, and it is a gigantic red star. It's the 10th brightest star in the sky, and it's one of the biggest stars that we know of. It's dying. That's why it turned red. It's 548 light years away, meaning it takes the light 548 years to get here. So is it going to explode, or has it already exploded 200 years ago and the light's that far away still? So looking back in time, what we're seeing right now is this giant star, what it was doing 548 years ago. So that is the essence of the James Webb. The James Webb is going to, it has a much bigger mirror. It's than the Hubble. You can see in this image, there's a person next to the Hubble, and the James Webb is almost 21 feet across, 18 segmented mirrors. This is what they look like in space, obviously much larger. The James Webb Telescope is, quite frankly, about the size of a big school bus, whereas the James Webb Telescope, sun shield included, takes up more space than a tennis court would, much, much larger. So it's got the ability to gather more light, so faint light from far away galaxies and stars, that then in turn allows us to look back in time. So this is a really fundamental piece of why are we doing the James Webb Telescope? Because we want to understand how galaxies were formed, how the first stars were formed, what was going on billions of years ago, like looking back 13 billion years. So what you're really doing is you're gathering light from a star or a galaxy that is very far away, and it left that object 13 billion years ago. I would pause now for a question if anybody has one, because I think that this part of it is something one needs to wrap their heads around, where actually you're looking back in time.
I don't see any questions in the chat, Larry, unless somebody wants to raise their hand.
I guess I can keep an eye on that, right?
Yeah.
So light stretches just like sound waves stretch as they move away from us. I think we're all familiar with a sports car coming at you. The sound is high pitched, and as it goes flying by, you hear a lower sound, the Doppler effect. So these galaxies far, far away are receding from us rapidly. So their visible light is stretching out, and it's becoming in the infrared region. So the James Webb Telescope is going to look at infrared light. That was a lot of people pushed back on that. They were saying, like, well, why are we looking at infrared light? The reason is that the objects that we're interested in, those light waves have stretched out and they're now in the infrared region. So to see back in time, we need to be able to gather infrared radiation, infrared light, as it were. Okay. Now I'm so sorry, I don't know what's going on. There we go. Infrared light also has a longer wavelength, and it has the capability to pierce right through dust and gases. So here's two pictures of the same nebula. And in the one on the left, it's a beautiful picture. It's a classic for amateur astronomers to do this. But the picture on the right, you could obviously see, was taken with infrared, and you can see many, many more stars, and you're not hindered by all the dust and gas. So infrared radiation is emitted by hot objects. So for the James Webb Telescope to work correctly, it's going to have to get very cold to be able to gather these very faint infrared waves. So the Hubble orbits the Earth, and it's in the sun half the time. I mean, in the sun directly almost half the time. So the James Webb Telescope is going to go out 1 million miles from Earth to a point people refer to as L2. And we're going to talk about that point in a minute because I think that's fascinating. This L2 point is in lockstep with the Earth, and the James Webb Telescope will be out there with its sun shield to the sun. It'll be pointing into deep space, and on the dark side, it will get extremely cold. And with this huge mirror, that will allow it to gather light from objects that are billions of light years away. All right, this is where I think people, if you don't mind, we're going to do a little fun math, some higher level math perhaps, or at least talk about mathematics theories and such. So where the James Webb Telescope is going to be is at a special point. It's like a balancing point. It's a balancing point caused by the relative gravity between the Earth and the sun. And there are these balancing points around every planet, particularly around Jupiter, because it's so big. So let's just talk for a few seconds about Lagrange points. I hope this is okay. I mean, I don't mean to go down the rabbit hole too far here, but I found this part fascinating because let's check this out. So this guy, Joseph Lagrange, he was born in Italy in the 1700s, mathematical genius. And in fact, he was a professor at age 19. He worked for a very famous mathematician called Euler. And he was around during the French Revolution, but setting the stage. This is a mathematician that doesn't have the benefit of any computers or calculators or anything. We're talking 1700s. And just by doing the mathematics, they came up with the theory behind these Lagrangian points or balancing points. Can you see my pointer on the screen?
Yes.
You see my mouse? Okay. So mass 1 is like the sun. Mass 2 would be like the Earth. And it's kind of like a teeter-totter, but there's no board. Between these two, there ends up being balancing points caused by the relative gravity of the objects. So far, so good?
Yep.
Now, these balancing points, they did this all just by theory. In other words, pencil to paper. They predicted that these balancing points would be there. It wasn't until the late 1800s, early 1900s, that people actually observed objects at these balance points. And since then, the United States and several other countries have leveraged these balance points for space exploration. It's also these balance points are the places for the famous space stations from science fiction. L3 is the point of where the invisible planet is. See, it would be opposite the Earth, that kind of thing that people talk about. This is kind of a picture in terms of gravity of the sun, the Earth, and these balance points. So what we're going to do is the James Webb Telescope was sent out to the L2 balance point, not the first time that we've put an object at one of these balance points. For instance, L1 at the balance point L1, which is between the Earth and the sun, we have several different satellites there that monitor the activity on the sun. So if there's a big solar storm, the particles from the radiation, the solar storm, will actually reach that satellite before it reaches Earth. And, before I leave that slide, I don't want to run too long, but I do want to point out that this is really important, having a satellite that's observing the sun. A couple of weeks ago, there was a big solar flare, and it ejected a bunch of particles towards the Earth. Those particles came towards the Earth, and we were alerted to that fact by these satellites in space. And quite frankly, it had very little effect on any of us, but it did knock out 40 of Elon Musk's satellites that are in space for doing internet. So understanding and observing the sun is extremely important. Okay, so they launched this, I want to be careful of my time. They launched the James Webb Telescope on an Ariane rocket on December 25th, and it went up, it cleared our atmosphere, it went out, heading out into space. And it's interesting, they calculated this perfectly so that it had one big boost, and it's shooting out in space 1 million miles, and they turned off, the engines are gone and off. And while it was floating through space, this satellite actually unfolded itself, unfolded the mirrors, and set itself up. And after a month, it coasted correctly into position at that balance point, all unfolded. Now, the next steps are, it's got 18 mirrors. So all 18 mirrors were pointed at a star, and it took an image, and this image here on the left has got 18, it's the same star, but it's 18 different mirrors. The object is going to be to then start to calibrate those mirrors and bring them together to where you finally end up on the right with just one spectacular, clear, clean image of one star. That will be the power of all 18 mirrors working together. This is the picture from the very, very first calibration. So there are 18, looks like there's 18 stars on here. That's all the same stars. The mirrors aren't aligned yet. It's heading towards that. Its main goal is to shed light on our cosmic origins and the universe's first galaxies and look for planets with the potential for life. And I lost an image in here. Uh-oh. Well, I don't know who it is. So that's where we're at right now, is the calibration stage. The James Webb Telescope has got to cool down. It's going to be operating at minus 380 degrees Fahrenheit. That's where it will be operating at, is operating temperature. You can actually go on the web right now. There's an app, and you can see the temperature, and it's down to about minus 350. So it's closing in on that. So there we go with a little bit of an overview on the James Webb Telescope and where it's sitting and why it's important. I hope that's what you were after.
That's excellent, Larry. In fact, we do have time for some questions. I see one in the chat already. I'll just mention that. Are the images from the JWST colorized?
Yes, they will end up being colorized. And in fact, quite frankly, the images from the Hubble are colorized as well. And the way you do that is when you image, like the Hubble images, it uses a series of filters. And so it filters, so it just takes a picture with the red light, then maybe the purple light, the green light, the blue light, and then it layers those together. It layers all those together and you colorize them. Amongst amateur astronomers and even professionals, there is an agreed upon means to colorize, and it's called the Hubble Palette. So it's a specific thing. There's a good reason to take our regular camera and take pictures of space. We would be disappointed, because if you think about your camera, it's got three different receptors in it, the three basic colors of the light: cyan, magenta, yellow. So red, green, blue, basically. And so if you're taking a picture of a distant star, that's fundamentally, you're only getting one of those colors. So you're only using 1/3 of your chip. So most deep space cameras are monochrome. It's just light. And they separate the colors with filters.
Okay.
So when you see a beautifully colored picture of a deep space, some nebula or something in space, somebody has manipulated that. They haven't. The colors are manipulated, but they're based on the frequency of the light going through the filters. In other words, you wouldn't purposely make something green if it came through a red filter.
Right.
That makes sense?
Yeah. Another question was, what was the name of the app that you mentioned?
For the James Webb.
Right.
I think if you just Google James Webb today, it's on NASA and it'll pop up. And I'm sorry, I should have had that.
Yeah, I have seen some of the images on Instagram, and I don't remember the name of the site, but I see them all the time because apparently I've liked a few of these things, so I can see them. And every time I see them, I'm just amazed at the brilliance of the colors and the clarity. It is amazing. I have a question. When you mentioned calibrating the 18 mirrors, yes, how do you go about doing that? I mean, how long does it take to like switch it from like 19 degrees to 18.5 degrees, that sort of thing?
So each one of those mirrors has actuators behind it that can move it in just micrometers. And so from the ground, from the Space Center, they will make calculations and then adjust, like the top of this mirror needs to go out. So there's an actuator that'll move that just in micron amounts out a little bit. Then they've got to let that all stabilize. I think I've seen that we should be getting good images in another month, but the really awesome ones, it'll probably take 6 months of tweaking each one of those back and forth, up and down, until you've reached your optimum.
Okay, question. Another question was, how long does it take to receive the images?
The images, the time it takes the light to cover that is, I think, about 8 to 10 seconds to get, in other words, for us to send a signal back and forth. I believe that's true. And so the images are, I'm going to have to say I don't know. I'm going to guess that they probably download to a satellite that then downloads in a burst to the space, the place that's actually collecting it all.
Okay. Another interesting question is, when you visit schools, are students allowed to view via a telescope, or do you just talk with them about how this all works?
I have 2 specifically solar telescopes. So yeah, if there's a teacher on there, I'm at Sunspot Larry at Gmail. I'm on Twitter at Sunspot Larry. Anyway, it's we look through 2 solar telescopes. One of them is a white light telescope that you can see sunspots and those kinds of activities. And the other one is called a hydrogen alpha telescope that allows you to actually see. These are common. You'll see pictures of these on the web a lot when they talk about the sun. It looks like reddish orange, and you can see the prominences coming out and so on. So those 2 telescopes, they're absolutely solar safe. They're big, heavy duty solar telescopes. In fact, the ones I have are even bigger than the ones I have at the State Museum.
Okay. One of our participants has indicated there is a James Webb tracker app. in the App Store, so you can find it
Thank
there.
you.
Obviously, you can also, Google the information. I'm sure it's in a few different places. I know that I've seen the Hubble images over the years, and now everything you see is basically Webb images.
Okay.
Fantastic.
I can put something back on. I can put something on there, right? On the chat.
Sure, of course.
It's jwst.nasa.gov is the web link. All right, let me look. There was another question. It was, how long will it last?
Right.
If it goes well, minimally 5 years, they're hoping. Hopefully it will last 10 years. The Hubble's been going for 31 years. Yeah. Here's the thing, that balance point I was talking about, the L2 balance point, it's not perfect. And so the James Webb Telescope is actually in a tiny little orbit out there to stay in a stable position. And it's using up tiny amounts of fuel to do that, but it's using up fuel nonetheless. Ultimately, when the fuel runs out, it will wander out of that position. So, okay, it's
I don't think there are any other questions unless somebody would like to ask a question. That was amazing information, Larry.
Thank you. That's very kind.
Yes. Yeah, jwst.nasa.gov for everybody.
Hi, this is Jerry Bright. I'm driving, so I can't text. But I'd like to know how electronics works at that extremely low temperature.
If you go to the NASA website, they have devoted an entire chunk just to that. And the amazing thing is there's a huge super cooled room that they moved this entire thing into. First they did all the pieces, then they moved the entire telescope into this room, and they dropped the temperature down even colder than what it's going to be at to be able to test everything. But all of the circuitry and it's not like copper wiring and that sort of thing. It's all high-end rare elements and so on that have these characteristics. This is why it's like $9 billion.
Okay. Well, Larry, thank you so much. That was an incredible presentation. And I know I'm going to get off of this and go straight to my phone and check out some more of the images. I think that we're going to go ahead and wrap it up. And I think that I don't believe we have any announcements, unless Mary, you'd like to make an announcement about the next speaker?
Yeah, no, I should know to do this, right? Hold on just a second. You ask me every time, and every time I flumble around. Okay, so, it's going to be great. Next week, Bentley Merle, who is a Rotarian, he and his wife trained dogs for the Southeastern Guide Dog Center. So he is going to be on with one of his dogs, and he will talk about training these sweet little animals for people with disabilities or blindness. So that's pretty interesting. So
Larry, did you want to say something?
I'm going to type it into the thing. But at Shaw Air Force Base, they're going to have the Shaw Air and Space Expo. It's a free air show on April 2nd and 3rd. And if you want to look at the sun, come on out. I will have my solar telescope set up there.
Excellent. Thank you for that.